So in section 11.4, we have a couple different objectives. The first one is to talk about something called conditional probabilities, looking at how we find that. And then tomorrow we'll focus on how do we use tables and tree diagrams to help us calculate conditional probabilities. So today, more focus on the table. Tomorrow, more focus on the tree diagram part. Okay? It says the probability of an event B will occur given another event A has already occurred is called a conditional probability. The probability that event B happens knowing that event A has already happened. Okay, it's called conditional probability. Conditional probability occurs when your events are dependent. So we've been talking about probabilities of independent events, A and B, when they're independent. Today we're shifting to that A and B when they're dependent. The new notation that you're going to see looks like that. It says we write the conditional probability of event B given that A has occurred as P, and then in parentheses you have B and then a slash and then A. Okay, that slash is read given that. So what is the probability of what is the probability of B given that A has already occurred? Okay. Tables and tree diagrams can help us find conditional probabilities. Tables make it very easy. Tree diagrams with our formula are not difficult. It's just a little different way of looking at it. Okay. Our first example says the table shows students by gender at 2- and 4-year colleges and at grad school in 2005. We pick a student at random. Okay, so we're just picking one student. We want to know the probability that the student is female given that we know they're already in graduate school. Okay, that given is going to narrow down your table. So when we look at the table, we've got 2-year colleges, 4-year colleges, grad schools. If it says given graduate school, then we are only going to work with that part of our table. All right? They're telling me to narrow down my focus. I know the student is in grad school. Now, what is the probability they're female? Okay? So we would need the number of females, and then we would divide it by the total in grad school. Okay? So this is why I said you probably want a calculator. We've got some bigger numbers to add up. Let's go ahead and add up our grad school students. We need to add 1349 and 1954. Okay. So our probability here would be our total number of females, 1954, divided by the total number in grad school, which was 3303. Okay. Let's go ahead and get a percent for that. 59%? Okay. All right. How is the next question different? What is the probability the student is female? This is not a conditional one, right? It's just a single event. We don't know what school that student is in. All right, they could be at a 2-year, a 4-year, or grad school. So we do have to get a total for everything. Okay, so we need the number of females compared to total of all students. All right. We got some calculator work going here. Well, let's break it down. Okay. Total number of students. Did we add all 6 of these numbers up? Anybody? All right, 17472. Anybody else get that? Okay. Now, total number of females. Then we just add this column, right? Total number of females. So if we add this and this and this, we got what? 9933. All right, 9,933. And then if we divide, we get, what was it? Anybody else get 57%? Okay. I do want to clarify up here in the first example. I wrote total number of females. It should say number of females in grad school. Okay? Because this was a conditional one. We already knew we were in grad school, so we were only looking at the females in grad school compared to all the students in grad school. Okay? In the second example, we needed all females, right? The whole column. All right. It says, what is the probability that the student we pick is in a four-year college given that the student is male? Okay? I'm going to pause the video. I want you guys to talk at your tables. What part of my table will I be using? Is there a specific column, a specific row? What is it that I'm going to narrow it down to? All right, the key to doing these with a table is really to make sure that you know what part you're narrowing it down to, okay? So you have to start with the given. And this says, what is the probability they are in a four-year school given that we know they're male? So we are going to narrow our chart down and only look at the column of males, okay? So we just want this. So we need a total for males, right? And then we're going to select the specific one we want, which was four-year schools. So we need that. All right. So we are going to be taking, what was it, 4324 divided by the total of all males. Did anybody get the total of all males? 7539. Okay. So 4324 divided by 7539 is another 57%. Okay, part B. Without calculating, given that a student is enrolled in a four-year college, what part of your table are you looking at? Given that they are in a four-year college, so we're just looking at that middle row, right? Is it more likely for the student to be male or female? So if we are just looking at this row, right, it's more likely that they're female. There's more females than males. Yes? All right, so the given is what you're going to narrow your table down to. And then within that row or column, you pick the one you want. Yes? Questions so far? All right. Our second example. It says Americans recycle increasing amounts through municipal waste collection. The table shows collection data for 2007. What is the probability that a sample of recycled waste is paper? How would we write this as P of B given A? What's B, what's A? It says, what is the probability that a sample of recycled waste is paper? Okay, so we would say the probability that it is paper, given that we know it's recycled? Yes? No? Does that make sense? Right? They've told us they're narrowing it down. What's the probability that if we take something that's been recycled, what's the probability that it's paper? Okay? So we need what on top? I'll ask a different question. What part of my table am I using? Recycled column. Okay? So I need a total for the recycled column. Go ahead and total that all up. 45.2 plus 7.2 plus 3.2 plus 2.1 plus 21.7. What do we get for a total? The bottom part. 79.4? Agree, disagree? Are we agreeing with that total? Okay, so the bottom is 79.4. Total of all recycled. And then we want the specific cell that has paper. So 45.2 divided by 79.4. And it comes out to be? Makes it easy for me to remember the answers, right? They're all the same. No, they're not always going to be 57%. All right. I am going to pause this. At your tables, I want you to do the got it questions, parts A and B. So for part A, we are looking for the probability that it is, what? How would we write that out? Plastic, given that it's been recycled. Okay? So we need to know from our table, we're narrowed down to the recycled column, right? So our denominator is still going to be 79.4. But now we want plastic, so 2.1 out of 79.4. Yes? Okay. For the second part, we want the probability that it is glass given that it's recycled. How much glass was there? 3.2 out of 79.4. We're not getting 57 for these, are we? No. Told you they're not all 57%. They're wrong? No. First one is what? Can you narrow it down one more decimal? About 2.6%. Okay. And second one? Okay. Questions about that? Okay. At your tables, using the same table up here of recycled versus non-recycled, I want you to create a problem. Okay. And it needs to be written out like this. Okay. Identify what your second event is given your first event. All right. Pick something. And then how would we narrow down our table? Okay. All right. This is what one of our groups came up with here. The probability that it's non-recycled given that it's plastic. All right. So what part of the table have we narrowed it down to? What's your given? Given it's plastic. So we have narrowed it down to just this row. Yes? The given is your narrowed down. It can be a row or a column. And then within that narrowed down piece, we need the non-recycled. Yes? So we would have to take 28.6 divided by, what do we have, 30.7? Does that make sense? So keep in mind that the given doesn't have to be a column. It can be a row. Okay? All right. Whoops. So for conditional probability, it says for any two events A and B with the probability of A not equaling 0. So A has to be able to occur. All right. If you're trying to calculate the probability that event B happens, given that A has happened, A has to happen. Okay. So its probability can't be 0. Our notation here says we need the probability of B given A. We can find it by taking the probability of A and B and dividing by the probability of A. Okay. Underneath here in red, I have rearranged this formula. What did I do? How did I rearrange it? It's the same formula, it's just written slightly different. Yeah, I just multiplied this over to this side. Yes? So instead of having a fraction, now I've just got a regular equation. Does it look at all familiar? What was the formula we had when we had independent events? The probability of A and B was the probability of A times the probability of B, right? Does it look almost the same? These match. Yes? These match. This, it's not divided by A, it's given A. This is for dependent, right? So it's very similar. We're multiplying the two probabilities together. It's just that our probability of B, if they're independent, has no effect on A having happened, right? That doesn't affect it at all. But if they are dependent events, my probability of B is going to be a little different. All right, it's like the example we talked about the deck of cards. If I leave a card out, I've changed my deck now, and that's going to affect the probability of that second thing happening. Okay, so if my events are independent, I can simply find the probability of B. If they are dependent, I have to adjust it because I know that A has already happened. Okay, it does not matter to me at all whether you use this version or you use this version. Okay, whatever seems easier to you is fine. I like the bottom one a little better just because it resembles my independent version. All right, but you can use either one. Okay. All right, so we've got two more problems to work through. This one says we want to use that formula. I know it's a table. We could do this the same way that we've been doing the other few examples, but I want you to see why that formula works. Okay? So, it says we have a utility company. They asked 50 of its customers whether they pay their bill online or by mail. What is the probability that a customer pays the bill online given the customer is male? Okay? So, what is A and what is B? A has to happen first, right? What is the probability that the customer pays the bill online given that the customer's male? So what is A? A is male, right? We're looking for what the probability is that they pay online, knowing that we've already picked a male customer. Okay? So the given is A, right? It's P of B given A, right? So male is our A value, and on paying it online is our B term. Yes? You have to identify what your A and B's are to set this up correctly. So the probability of A and B is the probability of A times the probability of B given A. Okay? Now let's rewrite it with males and online. So this is the probability. A we said was male. B is online. So we need the probability they are male times the probability that they pay online given they are male. Okay? So, looking at our table, can we figure out the probability they're male? From the table. We're going to have to do some totaling. How many total males are there? Total males? 20? So the probability they are male would be 20 out of how many customers total? 50. So the probability they are male would be 20 out of 50. Okay. Of those 50 customers, how many are male and they pay their bill online? 12 of them. Yes? Agree or disagree? We okay with that? All right. What they've asked us to find is this, right? That's our unknown, what we're trying to figure out. How would we solve this equation? If we're trying to get x alone, how do we get rid of that 20/50ths that's being multiplied to it? Okay, we could times both sides by the reciprocal, right? Or think of dividing it out. So we need to take 12/50ths times the reciprocal, so 50/20ths. The 50s would drop out. We get 12 divided by 20, which reduces to 6/10 or 60%. It is close to 57, but it's not. Yes. Okay. His question is, could we have done this like we did the other ones? And I said before we started this that yes, right? We could have done this the same way we've done the other two examples. If we had focused on that method, we said the probability online, given their male, we would focus just on the row of males and then pick the ones online, right? 12 out of a total of 20. Yes? What I wanted you to be able to see is that this formula is going to work, right? Is it longer in a situation where we have a nice table to work with? Yes, that took longer. But tomorrow we're moving into some tree diagrams where we won't have all of these little pieces, all these numbers to work with. And we have to use the formula. So I'm just trying to get you used to what that formula looks like. Okay? All right, the last one we're going to do. It says researchers asked shampoo users whether they apply the shampoo directly to their head or indirectly using their hand. So in other words, do they pour the shampoo in their hand first and then put it on their head, or do they just squirt the shampoo right on their head? What if you miss? That's a big question. We're not going to answer. All right. It says, what is the probability that a person responding to this survey applies the shampoo directly to their head given that the person is female? Okay. Talk at your tables. What is A? What is B? Okay, again, I want you to use the formula just to make sure we know how to work that for tomorrow. So the probability of A and B is the probability of A times the probability of B given A. You guys should write that down several times in your homework, right? Because that's what's going to help make that stick in your head. So we have identified that the given is our A, right? Whatever's given is A. So in this case, we want the probability that they are female and they apply it directly to their head. We're going to calculate that, the probability that they are female times the probability that they apply it to their head, given that we know they are female. All right. So, how many females do we have? We have 30 females? Yes? Total females is 30. Out of how many total people that answered this question? Our column of, or our row of males is a total of 20, so we talked to 50 people. So the probability that we randomly select a female would be 30 out of 50. Okay. Of those 50 people that answered the survey, how many are female and apply it directly to their head? Just the 6? Yes? All right. And so what we're trying to figure out is our unknown over here, right? So we're going to multiply both sides by what? So 6 over 50 times 50 over 30. Our 50s drop out. We end up with 6 divided by 30, which is 1/5 or 20%. Yes? Okay. Using the first method we talked about today, would we still get 20%?
Yeah, that's right.
So it says given females, we are only looking at this row, total of 30. The ones that apply it directly to their head, 6 out of those 30. Yes? All right. So there is your assignment, and we will finish up 11-4 tomorrow.